This first chapter, right, is going to establish a lot of very important things. This lecture here, in my opinion, is a lot more important than you probably realize. Vectors are a very important mathematical concept that we use to express a lot of things in physics. If you've had vectors in some capacity, fantastic. If you've not, I need you to really concentrate today, because this is stuff that can be easily taken for granted. And I will tell you this, based on my experience teaching this course, a couple things. Students just generally don't take vectors very seriously because, one, they don't quite understand them, and two, they don't see the importance of them. And this is evident when I teach Physics 120, and I have students that don't come from my previous class in 110, and they come in and, vectors are like, what's going on here? So here's what vectors are meant for. A lot of numbers that we deal with are single quantities. They're one-dimensional numbers. They can be expressed with a single thing. So, for example, the mass of an object. This thing is 20 kilograms. There's really no other information you can give about that. It's just 20 kilograms. A person's age, the temperature of an object. These are one-dimensional quantities. We have a name for those, and they're called scalars. There are a lot of other quantities, though, that need more information. They are multi-dimensional quantities. For example, the speed of an object. If you want to talk about how fast a car drives, well, you can say a car goes, well, like you see in the example here. Say we have an object that goes at 5 meters per second. Okay, fine. Well, there's a lot of ways that you can go 5 meters per second. You can travel 5 meters per second in a straight line. You can go up an incline. You can fall from the sky at 5 meters per second. You can travel in a circle at 5 meters per second. And those are all very different things. And one of the things that we're trying to do, especially in Chapter 1, is before we try to solve any problems, we have to make sure that we can properly describe motion, describe physical systems. And descriptions have to come first before we're going to even attempt to explain and predict behavior. Okay. So vector quantities are very useful for us. They are multi-dimensional things. Okay, an example of one is velocity. Velocity is a multi-dimensional quantity. You need to know what the speed of the object is, which is like 5 meters per second would be its speed, but you also need to know the direction. Are you going in a straight line? Are you going up an incline? Things like that. And that would be a more complete description of what the object is doing. Not only are vectors good mathematical things, which you're going to see more of later, they're also meant to be graphical things. They have a geometric representation to them. So what you see here is you see a vector. This green arrow that you see here is a velocity vector. It's a velocity vector because we labeled it as a velocity vector. Notice the notation. There's a V with a small arrow on top. That is the notation to describe a quantity that is a vector. And it's very important that when you describe quantities that are vectors, that you include this notation. This is absolutely necessary because it specifies the difference between a scalar quantity and a vector quantity. Okay? To say that the object travels at 5 meters per second and purely say that, that's the magnitude of that vector, which is also the scalar. It's speed. Speed is a scalar. We also have direction, which we can include, which is usually specified as some kind of angle, and that indicates direction. Graphically speaking, the green arrow has a length to it that is proportional to its magnitude and a direction, which, like I said, can be specified with an angle of some kind. Great. In this particular example here, I am illustrating a displacement vector. So a displacement vector is two-dimensional. It includes the distance traveled and the direction traveled. So this person, Sam, left their house and decided to travel 20 feet in a particular direction, which I guess we have called northeast, which is a little vague, to be honest. I'm going to make the assumption that northeast means 45 degrees with respect to east. There's a little ambiguity here, which you'd have to figure out what's reasonable. I think it's reasonable if somebody's being vague to assume 45, because if it's not 45, you would think they would provide you more detailed information, but we're going to go with 45 degrees. The overall displacement is called the magnitude of the vector. It's the length of this arrow here, and it's 200 feet. So this what's drawn here is the displacement vector for the person. The tail of the vector, which is the back part of it, is at the starting location, and the tip of the vector is where the person finishes. And that length there represents the distance traveled. Okay, good. Now, Bill sees what Sam does and gets like motivated, gets like hyped. It's like Sam left his house during the pandemic. Like, oh my gosh, what is he going to do? And then Bill sees this guy go 200 meters northwest and says, oh my gosh, I'm going to do this too. So he leaves his house and goes 20 feet northeast. And we can express Bill's displacement with a vector. Now I've labeled them S and B. And these two vectors are identical, okay? Because Bill is just a big, it's just a big fan of Sam here. So we have the same vectors. Now, what means they're the same? Two vectors are the same if and only if their lengths are equal and their directions are equal. So the vectors will be parallel and of the same length. One thing that is not important for vectors to be equivalent is that they are located at the same positions in space. One of my vectors is at Sam's front door, and the other vector is at Bill's front door. And that's not important when determining if vectors are equivalent. Vectors can move around and be placed anywhere you like. The starting positions and the final positions are not important. What only matters is length and direction. Okay, so Bill the fanboy here has matched what Sam does. Okay, and then when Bill gets to the end of his path, he finds the restraining order that Sam has issued against Bill. All right, well, that's a separate issue, I guess. All right, so let's look at different terminologies for these vectors. A and B are parallel to each other. Yeah, well, you know, Sam should move. Put it that way. Sam should move. All right, A and B, these are parallel vectors. Why? Because they point in the same direction. Easy. Part B, these are anti-parallel vectors because they point in different directions. Anti-parallel is a word, just so you know. I had some student tell me a while back that that's not an appropriate word. And I was like, dude, you need to calm down. It's just a word. All right, anti-parallel, opposite directions. And when you see this later on, what this will mean is one of these vectors are considered to be positive and one is considered to be negative, which you can see in the next example here. We have another anti-parallel example. We have the same vectors, vector A. We have minus vector A, which is the same vector flipped around. So an anti-parallel vector is one that is simply flipped 180 degrees, which can be indicated with a negative sign in the front here. Right? A and B are equal, same length, same direction, as you can see here. And then we have this nice fancy word, orthogonal. A is orthogonal to B. That's just a fancy term that means perpendicular, which by itself is a fancy term that means at right angles. But orthogonal is, orthogonal is a nice enough word that just makes it seem more complicated than it is, makes yourself seem smarter than you are, so we're going to go with orthogonal. Orthogonal. Okay. You can describe what?
Quick question.
Yeah.
So in example A is parallel to B but not equal to it because it's not the same magnitude, right?
You bet.
Got it.
You bet. Okay. All right. Okay. So what can we do with vectors? Well, we can do what's called scalar multiplication. When a scalar, a single number, is multiplied by a vector, it has the effect to increase or decrease its length, but not change its direction. That's the effect of a scalar multiplication. Okay. If you were to multiply by a negative scalar, it does affect the direction actually. So a positive scalar can either increase or decrease the length of the vector, and a negative scalar can also increase or decrease, but will flip the direction of the vector. All right, so that's the effect there. To add or subtract vectors. For example, why would we want to add or subtract vectors? Well, say, for example, we have a multi-step process by which Sam decides to leave his house. So Sam leaves his house, and he's not just going to go 20 feet northeast. He's going to go on a little bit of a scavenger hunt and explore the area. And what you can do is you can take each individual part of the trip, which you can express as a displacement vector, and you can add all of them up, and it equals the net displacement, which is the overall effect of what the trip entitled. It could be complicated what happened in between, but you could ultimately express with a single vector the beginning and end stuff. So if you add or subtract vectors, they will do something similar to a scalar multiplication. It either adds to the length or subtracts from the length. Now, just to be clear, right now we're only discussing one-dimensional vectors. When you have two-dimensional vectors and you have multiple directions involved, it's a little more complicated, and we will attack that a little later in the lecture here. But that's the effect of addition and subtraction, at least from a one-dimensional level. Oh, here we go. 2 dimensions. What if you have a two-dimensional vector? How the heck do you add that stuff? Here's how you do it. You take your two vectors. Now remember, the placement of the vectors is completely irrelevant. The only thing that matters for a vector is its length and its direction. So we may have two vectors here, vector A and vector B, right? And we could draw vector A out any way we like, but what you want to do with vector B is you want to redraw vector B in such a way that it is attached to vector A. And the way we do this is it's just like you drawing out a literal path. Vector A is drawn, vector B being next is placed onto the tip of vector A. Make sure you preserve the lengths and the directions of things. If you've done that, then to compute the sum of vector A and vector B, you go from the tail of A to the tip of B. I have a new vector drawn here, happens to create a triangle, and the vector that's drawn at the bottom here is the vector A plus B. So if I go back to the situation of displacement, Sam may have decided to walk in the direction of A. You know, his first part of his trip was vector A. The second part of the trip was vector B. And then vector A plus B is the net displacement. It's the one vector as if you just went from the beginning to the end and you just cut out all the intermediate stuff. Because this expresses ultimately where you are from where you started. Okay, and it's not just displacements. There's so many things, speeds, forces, all that stuff.
Did he cut out again?
He cut out again.
Yeah, he froze.
Your microphone.
We
Sorry.
lost you.
I know. I mean, I think it's not Zoom. I think I'm phasing out of reality, and that's what you're experiencing, which sucks because if that happens again, I may not be able to teach in this universe. I may have to teach. I don't want to think about that.
The little bar indicator for you like turned red, so I think you just lost connection for a sec.
I think it's probably a conspiracy. I think Spectrum doesn't really want me to teach this stuff. I don't know. I really don't know what's going on here. So thank you for your patience, though. It's weird because what happens is you guys start complaining about something, and then 20 seconds later is when Zoom tells me something's wrong. So I don't know. The upside is this. The upside is this. I'm recording the lecture. So worst case scenario, my recording has nothing to do with Zoom. I use separate software to do it, and I edit it later, so. Yeah, I do, Melker, I know I can mess with the channels, but tell you what, the problem is that I got a lot of kids. I've collected a lot of children in my life, apparently. And we're all on Zoom. Everybody's in a classroom right now. I'm on a classroom. And, I mean, I mean, unless I get like PHYS or something, I think this is my lot in life here. Yeah. I mean, I'm in the class and all my kids are in classes, so. Yeah, pandemic life is pretty cool. Not really. It sucks. I have a question for all you. All right. So, here's vector P and vector Q. I want to add them. What's the resultant vector?
Is that A?
A.
Well, put it in the chat. Put it in the chat. Sorry, put your letter in the chat. It could be a bandwidth issue, I guess. I just don't know what causes the spikes, though. That's the thing. I guess I'm not monitoring what all of my kids are doing either, so who knows. A lot of A's, a lot of C's. A little bit of B coming in now. Oh my goodness. What do we do here? So many different letters. Q? What's going on here? You guys are losing your mind. All right, what do we do here? Here's the rules. Before I show you the answer, you take the first vector, vector P, leave it alone. Take the second vector, Q, attach it to the front of P. And then you connect the back of P to the front of Q. That looks to me like A, if I'm thinking about it. Yeah, I'm thinking it's A. Oh, it's A. It's A. Look at P, look at Q. We connected them. A is the resultant vector. Nice. Any questions about that one? All right, let's keep going. Vector subtraction. We're going through elementary school, people. We're doing first grade again. With vectors, though. It's not first grade. Okay, how do we do vector subtraction? Guess what? Let me show you something that's going to blow your mind. It's going to blow, it may not blow your mind, but it should. Okay, if I have A minus B, you know what that is? That's A plus a minus B. What's minus B? Minus B is the B vector flipped 180 degrees. So what is vector subtraction? It's vector addition. You just take the second vector and you flip it. That's how you should think about vector subtraction. I think personally it's easier to think about that way. There's another way to think about it, and for those who've had vectors before, maybe you know about this, but personally I think that it's easiest to think about vector subtraction in this manner, because there's consistency here, right? Just learn vector addition. And then to do vector subtraction, just know to flip the second vector and then just do vector addition. Personally, I think that's easier. You might know something different, and if you do, by all means, do it. But I don't like the other method for subtraction because it is so radically different from addition, and I care about consistency in the problems. The other way to do it, just if you're curious, is you just attach the tails of A and B to. I am seriously considering just like a megaphone. And then if you could crack your windows, assuming you're in Lancaster or Palmdale, you're probably hearing me. How about we do that? That might be better. I'm a little sick of it. Zoom. I don't know. There's a million issues. I mean, the laptop they gave me is garbage. It's like garbage. Like I put on a virtual background and my computer starts to turn red because it's going to explode from overheating. Yeah, I don't know. All right. My apologies to you. I'm going to have to edit this video so much now. So many disruptions. Anyway, okay. So anyway, this is the approach that I personally like to take. The other approach is the following here. You take A and B and you attach their tails together. And then you draw a line that goes from B to A. I don't like that because it's just so different from addition. I don't think it's beneficial to like create a completely different set of rules for something that is so similar. So that's why I don't like to do that one. It's okay. All right, anyway, let's go over the vector subtraction here. There's A. There's B. I flip B. You draw out A. You attach negative B onto A. And you connect from the start of A to the end of B. So again, it's identical to addition with one additional little step. Take that second vector and flip it. Easy, I think. Easier than other methods. Consistent, very important. There we go. Awesome. If you're wondering, ooh, what are we going to learn about multiplication division? Or not, don't worry about it. If you care, maybe at the end of the semester I'll clue you in on, because after this, if you want to talk about multiplication stuff, that gets into linear algebra, which we don't need to know about. Don't worry about it. All right, wait, where am I here? All right, people, another question for you. What is P minus Q? Which direction is that? Aw, bless your hearts. Look at all these answers that are right. D, aw, man, making me feel good right now. See, you guys struggled a little bit on the last one, and then I explained it, and then we did a new one, and you all got it. This is called learning. This is called I'm teaching good right now. I'm happy with myself, and I'm happy with you. We're all happy right now. There's light, people, in 2021. And it involves physics. It is D. Fantastic. What did we do? We took vector Q, we flipped it. We stuck it on the P, and we drew out from the end of P to the start of P to the end of Q. Got it. Now, vector subtraction is a big deal for us. You know why? Because acceleration is the result of the difference between two velocity vectors. Later on, not today, later on meaning Tuesday, by the way, we are going to have to figure out acceleration vectors. And can you not, kitty? My cat is, my cat is harassing me right now. It's ridiculous. With you. Anyway, so the vector subtraction is going to be a really big deal for us because we are going to work out acceleration vectors from velocity vectors. And that's a really big part of explaining motion. So we're going to do that later. Why are you bugging me? I'm trying to teach right now. All right, so here's some other techniques that I want to make you aware of if you find it important to do this stuff. The commutative property applies to vectors, which means you can add A and B together, or you can add B and A together. Doesn't matter, you will get the same result. Which leads to a very interesting rule for addition of vectors called the parallelogram way to add things. You can draw A and B out to form a parallelogram, and the resultant vector is the diagonal of the parallelogram. No, the fact that I'm still teaching on Zoom right now means my cat is not involved, because if it was involved, my connection would cut out, and I would lose internet for an entire week. I am at the mercy of my cat, and apparently he still approves of my role in this house. Because otherwise my internet would be out. I'd probably would be clawed up or something. I don't know. But cat makes the rules. That's how it goes. All right, so associative property. The order by which you add things does not matter either. We can add A and B together and take the result and add it to C. You can do it in a different order. So, nice to know. The reason I mention this stuff to you is because these are little convenient tricks to help speed up problems if you can remember them, but ultimately they don't really matter. Okay, I'm going backwards. Okay, so let me try to scroll the other way. Here we go. Now, let's talk a little bit more about how we describe our vectors. Coordinate systems are a very important aspect of drawing out vectors, because it helps you to put numbers behind your graphical representations. So, you are familiar, obviously, with the Cartesian coordinate system. To remind you, we have names for the different quadrants. So starting from the x-axis, if you imagine an angle that can be drawn in different quadrants, the upper right quadrant is called quadrant 1, and then it increases as you go counterclockwise. So the upper left region is quadrant 2, quadrant 3, quadrant 4. Now, when I describe vectors, I might describe this is a quadrant 2 vector. And what that means is the direction points toward quadrant 2. It doesn't mean it's in quadrant 2. Remember, the position of a vector is unimportant. If I describe a quadrant 2 vector, it's a vector that points in quadrant 2. Let me show an example of that. Here is an example of a quadrant 2 vector. Right there. That's a quadrant 2 vector. The fact that it starts in quadrant 4 is irrelevant. That doesn't matter at all. It points up and to the left, which is quadrant 2. Okay. This is a quadrant 3 vector. That's a quadrant 3 vector. It points down and to the left. Okay. Here's a quadrant 4 vector. Let's go. All right. Any questions about that? Oh my God. Really? Really?
I got a question.
Why is my internet so shitty? I don't know.
No, not
Oh,
even.
okay, sorry.
So, what if like the one that starts in quadrant 4 and goes into quadrant 2, what if the magnitude doesn't take it into quadrant 2?
Doesn't matter. It
Yeah.
doesn't matter. It's not about position. It's about direction. So here's another example. This is a quadrant 2 vector right here. Check it out. Bam. That's quadrant 2 right there.
Got it.
It points that way.
I see.
Remember, I can't emphasize this enough. Positions do not matter. Only length and direction. All right, cool.
What if it just points straight up?
We have another way to do that. We don't talk about quadrants. I'm going to eventually reveal to you later things called unit vectors. And so give me about 10 minutes to get to that. You have a good point, though. That is just give me 10 minutes. Give me 10 minutes, all right? Good.
Will we ever,
Okay.
I actually had a quick question. Will we ever have like one with an angle? Because I see
Oh
one on
yeah,
the
you
quadrant
typically
one.
will. You typically will have one of an angle.
Will it be like specific? Like, because it could possibly be on quadrant 3. Let's say if we were doing like that angle one, right?
Yeah.
And it was pointing to quadrant 2.
Yeah.
Will it give extra detail on whether to start from quadrant 1 or 3?
Okay, so the best way for me to answer that question is to hold on. I'm getting to it.
I understand.
I love these questions. You guys are being awesome right now because all the questions you're asking me are things I want you to ask, and I will answer them by the end. So keep up the questions. I absolutely love it. This is a sharp class so far. I mean, I don't know. Maybe I'm just in a good mood, but you guys are asking the right questions. But I'm gonna get there. So fantastic. All right. So now I want to put numbers behind my vectors now. I want to put more concrete numbers. And so there is an alternative way that we can express our vectors, and that is through something called vector decomposition. Now, what vector decomposition is this? Check this out. I got vector A right here. Okay, it's a first quadrant vector, points up and to the right, has a length to it, arbitrary length, doesn't matter. But according to the rules that we just learned about vector addition, I could express this vector as a sum of two other vectors. Those two other vectors are orthogonal. I can express this vector as the sum of a vector that only has an x direction and only has a y direction. So look at this little thing up here, this little notation. This is a big deal. Vector A can be expressed as the sum of a vector in the x direction plus a vector in the y direction. Now, if you complete that sum, you'll end up with A. Now, why do we do this? Because when you have to combine vectors together, it is so much easier to combine your vectors together if they all have the same directions to them. If you take all your vectors and break them into x components, you can add them all up individually. If you add them up, if you have all y components, you can add those up, and then you can put a new vector together again. And vector decomposition is extremely important for this class and every other physics class you will take. Really, really, really important. I cannot emphasize enough how crucial it is that we do this. So the rest of the lecture here is going to delve into how we do this. Okay, so let's talk about it. Clear. Moving on. Come on. Okay, here we got some examples here. We have vector A. And we're going to break it into its components. Now, we have a coordinate system down here, so we can assign actual lengths to the vector. And it looks like this vector up here can be comprised of an x direction vector that is of length 3 and a y direction vector that is of length 2. Those two vectors, when added together, are identical to vector A. And so we call these two the component vectors. We say that a sub x is 3 meters and a sub y is 2 meters. Okay. Now, for vector B here, it's a second quadrant vector. Okay. A quadrant 2 vector would have a negative x component because it points in the negative x direction. So here, b sub y is 2 and b sub x is negative 2 to indicate that it's a length of 2, but it points in the negative x direction. So the negatives here are all about direction, which is true of the vast majority of negative signs that we deal with in physics. Negative signs almost exclusively refer to vector directions. The only exception I can think of off the top of my head is we also use negative signs in electricity and magnetism to specify negative charge, which, however, though, is closely tied to directions of electrical forces and fields. So it's very closely tied to that. But if you have a quadrant 2, 3, or 4 vector, then there are components that are negative. For example, a quadrant 3 vector has both x and y components negative. Right? Okay. All right, what are the components of this vector? Now, I've particularly drawn this vector, and I placed it so that its tail is on the origin, which, by the way, is always a very smart thing to do. I could place this vector anywhere I want to. It's just easier if I put the tail at the origin. So I dare you, in the chat, tell me what letter you think is correct here. What are the components of this vector? Now, just to be clear, the way we write the components out would be similar to the way that you were to specify a point in a Cartesian coordinate system. The first one is the x and the second one is the y. So, come on. Time to impress me. You're not going to impress me. A lot of B's. I like it because it's right. So if we call this vector A, we would say a sub x is 2 and a sub y is 3. Fantastic. Excellent. What about this one? Smarty pants. Think you're a hot shot for the last one? Oh, everybody's so quick now. Nah, I think you guys are being cocky now. D's donut. My goodness. This is a physics class. You don't call them donuts. We call them toruses. You got to get with the lingo now. When you go to the store, say, I would like a maple torus. And they'd be like, I don't know what you mean. And you're like, I figured you didn't know what I mean. I took physics. It's called a torus. And the person's like, can you leave the store already? You're like, okay, fine, sorry. Then you go to the Dunkin' Donuts drive-thru where they have really crappy donuts because you decided to make a fool of yourself in a place where they have good donuts. Anyway, sorry, the answer is D. Excellent. All right, so x component's 3, y component's -4. All right, you're getting it. You're getting it. I'm liking what I'm seeing here. Who's pulling up in my house? Oh, Instacart. Okay. I was like, somebody's pulling my driveway. I'm about to hit pause here. What? Oh, Melo's back too? Okay. I was sorry. I was like, I'm sorry. I'll be back. I need to get my baseball bat and tell somebody to get off my driveway. But it's Instacart, so I guess I kind of like wanted them to do that. So anyway. All right. What's up with C here? C is a quadrant 2 vector. What do we got here? I don't know. Looks like quadrant 2 should have a negative x component, right? So it's not A or C. What are you guys telling me? B? D? Come on, people. Aw, I was so proud of you, and now I'm disappointed in every one of you. Whether you got it right or not, I'm so disappointed. Who is that? What are they doing? Who is this? Neighbor? Who's neighbor? Leave. When I sit here, I look outside my house, and all these people, a lot of people driving up, stopping. I don't do that. Don't drive up my house and stop. All right, it's D. Why? You know what? The position doesn't matter. Yeah, I know someone's at the front door, Alexa. Jeez. All right. 4 to the left, -4. 2 up. Doesn't matter where we start. Doesn't matter where we start. Well, no, there's some car. It said neighbor on it. And it drives up and like, I don't know if you're my neighbor or not, but you need to get the hell out of here. Don't pull up my front of my house like that. I don't think so. Don't like that. Okay. Callista, I've had that doorbell for a year. I can't get it off. I got my Ring at Christmas time. So we're like, oh, let's put a Christmas jingle on. Great. I can't get it off. I'm listening to that freaking Ring in July. I can't figure it out. Sorry for my loss. Thank you. It's horrible. When somebody rings the doorbell, I go outside and say, listen, I know you don't know this, but don't never ring my doorbell again because I cannot change the ring on it. And they're always like, dude, you are strange. All right. Okay. Anyway, let's keep going here. Almost done. I got half an hour though. I got a lot of time here. Okay. Now, how do you go back and forth between the two systems? Because there are two systems here. There are two ways we express vectors. There's component format, and there's what we call the magnitude direction format. Now, magnitude direction format is a descriptive format. In most cases, that's how you will be told about vectors. You'll be told there's a car traveling 30 meters per second, 45 degrees northeast. That's a description. That's the magnitude direction format. You need to put that generally into components in order to do mathematical things to that. So we need to learn how to go back and forth between the systems. Here's how we do it. If you are presented with a vector in the magnitude direction format, meaning you have a magnitude and you have an angle, the way we would go about doing it for this particular vector that you see here is we identify the fact that that vector can be the hypotenuse of a triangle, and the legs of the triangle represent the components of the vector. So using our knowledge of trigonometry, we can specify that a sub x would be the magnitude of the vector a times the cosine of the angle that's given here. And a sub y is a sine theta, because again, that's the opposite side. So if you are given the magnitude and the direction of your vector, this is how you would go about placing it into component format. A cosine theta, a sine theta. Okay. Now, what if you had the other situation where you are given the components and you had to work backwards to figure out the magnitude and the direction? Well, we still, again, utilize trigonometry. If you have the legs of your triangle, to get the hypotenuse, which would be the magnitude, you would have to use the Pythagorean theorem. So a is equal to radical ax squared plus ay squared. And then the angle would be determined by an arctangent. Whereas the arctangent, at least in this format, is the opposite over the adjacent as an arctangent. Now, I want to make sure one thing is very clear. What I'm showing you right now is applicable to a quadrant 1 vector in standard form. Okay? Quadrant 1 in standard form. There's little variations you would need to make if you have other quadrants or if you have a non-standard angle. But let's get into that. Let's do it. Here is an example of a non-standard angle. Angle phi here is defined with respect to our vertical axis, as opposed to the last example where we define things with respect to our horizontal axis. This is very common. A lot of times the angles that we're given are not angles in standard form like you used to in your math courses. Sometimes we may be given angles that are a bit different. So what are the differences here? Here are the differences. The components change. If our angle is respect to our vertical axis, then the y component is not based on sine. It's based on cosine because the y component is the adjacent side. So you don't want to, what you don't want to do here is you don't want to associate x with cosine and y with sine, because that makes an assumption about your angle. What you want to do is you want to associate your cosines with whatever the adjacent side is. And in this case, the adjacent side happens to be a y. The sine function is associated with the opposite side, which in this case happens to be x. So our components are different here, right? B sub y is negative b cosine phi. Negative because it's a fourth quadrant vector and it points down, which is negative. And the y component is the adjacent side of this triangle. Okay, what about x? B is the magnitude, sine is the opposite side. And so we give it there. And it's positive because it points to the right, which is positive. Okay. Now, question for you here. We have a third quadrant vector with an angle that is defined with respect to the negative y direction. So how would I determine my angle? It's an arc sine, but you got to be careful. How would you compute it? Oh my goodness. You don't know. That's okay. That's okay. As you guys fill in, since I'm going to draw some things. I'll make that a little thicker. Make it real thick. There we go. There we go. Now, if I want to know this angle, I want to use my tangent, right? The definition of the arctangent is opposite over adjacent. That is always true, by the way. Okay? Tangent is opposite over adjacent. Always. What you sometimes need to figure out is, what is opposite, though? Is that x? Is that y? That's the challenge here. So one thing that's consistent, never changes. Tangent is opposite over adjacent. But opposite can be x or y, and adjacent can be x or y, depending on how you define your angle. In this case, the opposite is x, and the adjacent is y. And so it looks to me like C is correct. Now, I know, you look at A and say, well, professor, this is a third quadrant angle, and the x component and the y component are negative, and therefore the negatives cancel out. So is not A the same as C? And I would say, okay, you're being a smartass right now, which is, you're not wrong. You're not wrong. I would say strictly, though, the answer is C. Why? Just for completeness sake. Yes. So I have my vector here, and I drew a triangle, okay, that shows the components. This component at the bottom here is parallel to the x-axis. It's the x component. Let's write it in here. C sub x. This one right here, C sub y. That's how I do my, that's how I'd have to do the subscripts, because Zoom doesn't allow for any sophisticated text. There's my components. This component is parallel with y, this is parallel with x. Now these are negative components, and when you throw things into your arctangent, You don't want to throw in negative signs, because what you get out of the arctangent may be confusing. It's important that you always put in positive values. That's why C is actually more appropriate as an answer. A is not technically wrong, since both components are negative and they would cancel out anyway, but you should say C. Okay. I did not have to draw my triangle this way, by the way. I could draw my triangle like this. I'm gonna do green instead. I could draw it like this. I didn't have to draw it in any particular way. So I could draw it like this. This could be my, no! I selected green. Gosh, zoom. No, green, blue? It won't let me, it won't let me. It just won't let me. I can't do it. Oh, now I can do it. What a terrible, I can't do blue, I already have blue. Green. Thank you. What a terrible day. Here's another triangle I could draw. They're the same though. They're completely the same, because guess what? This component here is the same as this component. This component is the same as this component. Remember, position doesn't matter, right? So I could draw that triangle too. You get the same answer. You get the same answer. All the same.
Professor, which angle would we look at if we draw the green triangle?
Well, I mean, if you're given this angle, I guess you're going to give yourself more work, which don't do, but you'd probably want to specify this angle, I guess, and it would be the complement of phi. Or you could be a real weirdo and say like, oh, look, this angle is the same as phi because they're alternate interior angles, or I don't know, however you say that. But then why are you doing that? Just do the red stuff. I don't know.
Okay, thank you.
Professor, I was wondering, I wanted to ask a quick question. Which one was classified as opposite in this case when it comes to tangent?
The angle that's opposite is the one that does not touch the angle. So this side down here is the opposite. The adjacent is the leg that touches the angle. So CY is the adjacent one here, and CX is the opposite.
My bad. Can you repeat that one more time? I couldn't.
Yeah,
hear you.
sure. Oh my
Please.
gosh. Okay, keep going. Okay. Let me do it again. The side that touches your angle is the adjacent side. There's always a leg of a triangle that does not touch the angle, and that's the opposite side. So CX is the opposite here, and CY is the adjacent here.
Okay, I understand. Thank you.
Any other questions? All right. So let's start putting some more numbers here, because somebody earlier had a question like, what if it's on the axis? Well, we can handle that actually. Let's do that. So now we're specifying components here. Great. And I did mention at the start that the reason for the components is we can break our vector up into two component vectors. Well, those are ultimately vectors, so let's go ahead and specify them as vectors. And the way we do that is with the use of what's called a unit vector. Now, we have two unit vectors that we're going to work with now. One is called I hat. That's what the name of this is, I hat. This little symbol on the top of it is what we call a hat. I hat, J hat. I hat, by definition, is a vector of magnitude 1, and it points in the positive x direction. J hat is a vector that is of magnitude 1, and it points in the y direction. Okay? And if you want to specify, for example, say you have a vector that's along the positive y-axis and it has a length of 3. You would call that vector 3j hat. It's like we're specifying a scalar multiplication. It's 3 times the j hat vector. So that means the magnitude is 3 and it still points along the positive y direction. We won't really call that. You wouldn't actually have a name in terms of a quadrant. You wouldn't say it's a quadrant 2 or quadrant 1. There's no need. If you simply say like 3j hat, it's understood what that vector looks like. Okay? So the unit vectors are how we're able to take our components and actually turn them into vectors. So, for example here, once you figure out your a and y components for your vector, you can simply attach the unit vectors onto them and they automatically become vectors. So now we can actually specify an a sub x vector and an a sub y vector. And now we have this real juicy stuff down here. Ooh, this is good. I'm excited. Look at this. A is vector. You can decompose vector A into vector x and y, which now we can further specify in terms of unit vectors. Do you feel that tingling? Oh no, come on. Come on. I'm waiting for Zoom to tell me. Is Zoom not going to tell me? You know what I should do next time? Is I should try to replicate freezing. I'll try and see if I trick you. That would be fun. I'll and then I don't know, whatever. Okay. I don't like it personally. Okay, anyway, so that's how we do this. All right. Now, question for you here. A lot of questions. Vector C. How would you write it? How would you write it? Okay, I think all right, I get it. It's B. All right, I get it. It's B. You guys got it. You're learning. I'm happy. I'm doing my job. I'm glad. Did it crash? It's the worst day ever. It's B. You're right. Second quadrant vector. Negative x component, positive y component. The vector extends 4 in the x direction and 2 in the y direction. That is some nice stuff right there. That is good. I feel all cozy right now. Right, so guess what? One of the reasons why we're doing this, because guess what? All the things I talked about so far are so easy to do when you do things in components. Do you want to add vectors? Don't worry about drawing them out. You just got to add the components up. You take, if you have vector A, B, and C, you want to add it all up, what do? You just take the x components, add them up. Take the y components, add them up. And that's your new vector. If you want to subtract vectors, you just do it with the components. If you want to do a scalar multiplication, you just scalar multiply the components. The components make the mathematics way easier. That's why we do it. Okay. So there are two aspects to this. There are the conceptual side of things, and there is the mathematical side of things. The mathematical sides like components. The conceptual side wants to keep visuals and magnitude and directions, and they're both valuable, and they both have usefulness in what we do. We just got to make sure we can translate between the two systems. That's the point of that. So I got a couple of examples before we wrap it up here. Let's just delve right into it. Give me a minute to bring them up because I forgot to do that. Vector A, B, and C. Now, when I did things in PowerPoint, it's not so simple to put the little arrow on top, so I just put them in bold. Just because PowerPoint's a little lacking in that area, but anyway. Vector A, vector B, vectors. I just have vector A and vector B. Vector A is 4i hat minus 2j hat. Let's draw that. I draw that down here. A goes over 4, down 2. That's the vector. Vector B, negative 3i hat plus 5j hat. Well, okay, so going 3 to the left and 5 up. There we go. That's my vector. And I want to know what vector C is, which is the sum of vector A and vector B. So let's go through the steps here. Let's write C in component format. Great. So that's going to require me to take vector A and vector B and to express them in components and add their x and y components together. The x components are going to be 4 minus 3, which is 1, right? And then the y components are going to be negative 2 plus 5, which is positive 3. And you can see right here, that is what vector C is. It's I hat plus 3j hat, which I have drawn here, okay? So you can kind of see if I were to attach, say I were to detach vector B here, okay? If I detach vector B and throw it onto A, you can see here, well, that arrow, that's a little unnecessary. Come on, let's try that again. If I draw vector B, it looks like this. This is the same vector, it's same length, same direction. That's vector B right there. Right. Draw a coordinate system and show vectors A, B, and C on it. I just did it. I already did it. What is the magnitude direction of C? Well, I have my component format, but if I want to determine the magnitude direction, I'm going to have to use the Pythagorean theorem. So the magnitude of the vector is radical 10, whatever that is, 3.1, whatever. And then the angle. Now, I did a big boo-boo here. I messed up. Bad. Okay, let me try to rectify my error here. Here's what I did that's really bad. I don't have an angle labeled anywhere. And if you're asking me if I'm ashamed, I'm not. But I feel bad. So let me put the angle in first. I can't zoom in here. What's wrong with you, Adobe? If that's your real name. Okay. What the heck is going on here? Okay, so I made one little mess up. Here. Oh my gosh, everything is chaotic now. Okay. So, stop. Just stop. Okay, so I don't have an angle specified. So yes, I did do an arctangent here, which was cy over cx, and I got an angle 72. But here's the thing. You got to specify in a picture what your angle is. You really need to. Because you got to be super clear about what you're trying to describe. And by the way, everything we're doing right now is mostly just descriptions. So this is my angle right here, actually. It's a standard angle, but it does need to be specified right here. I'm trying to draw an arc, but it's hard. That's theta. There we go, theta, right there. So you really ought to label your angles when you determine them, because there's a lot of ways to talk about angles, right? You can define them in so many different ways. So if I do this, to really make this super complete, I should show that the angle I'm referring to here is this. So this is my angle in magnitude direction format. And it turns out that these two things here, by the way, I hat plus 3 j hat and radical 10 and 72 degrees, these are identical. These are two different ways to express the same thing. One is component format and one is the magnitude direction format. Okay, let's do this last example now. Let me zoom out. All right, I want to find vector B if the sum of A, B, and C is equal to the unit vector j hat. So I have drawn here A, B, and C. So the first thing you ought to do here is to specify what those are in terms of their magnitudes. So you can algebraically solve for B here. B will be j hat minus A minus C. That's perfect. You can do that. And so what is A? A is 4I hat. C is minus 2j hat. So if I plug all that in, I can see here that you can combine j hats together. There's only one I hat. When you combine I hats and j hats together, it's just like combining like terms, you know, in math. So this ends up being minus 4I hat and plus 3j hat. All right, cool. So that's the component format. Now I need to figure out what the magnitude direction is. So I'm going to use the Pythagorean theorem. 4 squared plus 3 squared. That's going to be 5 for my magnitude. And my angle, oh, I was a good boy this time. I actually put in my notation here. This is the angle I'm referring to with respect to the negative x-axis. So as long as I do that, when I work out my arctangent, it's clear what I'm referring to because it refers to the picture. So the arctan of by over bx, and oh, you know what? I'm never going to escape making mistakes here apparently. So the b component, right, for x has got to be negative, is negative, but I got to make it positive. So I should put a little opposite value here, just to be super consistent, because you don't want to throw any negative signs in here. The negatives didn't matter in the Pythagorean theorem, right? Because you're squaring things, so they're always positive. But in the arctangent, just make sure you make everything positive. That's just the rule. So this 4, you know, it's a negative 4, but I have to make it a positive 4, and I get 37 out of that. Well,